Okay, heaps. A heap of fun. So funny. So, what is a heap? Well, to put it simple, a heap is just a tree-based data structure very similar to a binary tree. It's going to look something like this. I'm going to hide this again, but just keep this picture in your brain because this is, what it looks like. You got values that are hooked up to each other like this. So pretty much, it's like a binary tree, but it's fundamentally different because a binary tree lacks organization while a heap requires it. And that there's a fancy term for that, and it's called, let me write it up here, priority. Exclamation point, underscore, oh, not underscore, underline. So pretty much all priority means is that a certain value is going to be on the top of it. In this case, on the top of the tree. It's going to be higher, closer to this parent node right here, due to some condition. Let me erase that. So, cool. It's a binary tree with more structure, but what can it be used for? And pretty much, it has its uses, but they're quite specific. And the main two is pathfinding and sorting. So, actually, I want to erase this. Let me pull up my grid. I got my grid. Say hello. His name is Bernie. Oh, I missed the I. This is Bernie, the grid. Hi, Bernie. So, pretty much we're trying to traverse through Bernie here. We're trying to go from red to green. Using a heap. So, I'm going to demonstrate that. So pretty much how this works is that it's just going to, every single time, starting from here, a path is going to break off and it's going to try and find the shortest path. So here we go. It starts from here, goes there. It's going to start from the top. It's going to go in each row. That's how it's going to work. So did this row first, and there's nowhere else it can go. So it's going to go and do this one, this row again. So it's going to break off and go up this way and this way. Technically, this one would come first, but and it's not that huge of a deal. And then it's going to do this one. And then it's going to go back to this one. It's going to move up. It's going to move right. It's going to move right. Oh, and I forgot this one. That one's going to move up there. And then this one's going to move right. And this one's going to move right. Oh, why isn't it working? There we go. But we just found the path. We reached the area that we want to go to. And I'll explain to you how it works in a second. What color am I feeling right now? I'm feeling pink. Bernie's feeling pink right now. That's what he was telling me. I could hear it. I could just hear it. I'm gonna do that. There we go. That's the shortest path. Isn't that crazy? Bernie, you're so smart. So, pretty much what happened here is it used a heap. And what it used was a min heap. So pretty much it was just making children until it got to its path. And then the first one to do that was going to return that child. So in this case, it took 3 steps. So the third child of this red one that went in that specific path is going to be returned. And that's going to be the path and how long it took. So I'll draw that out real quick, actually. So here. So here's the red. It can go in 2 directions. And we know this path is obsolete. I'm not going to visualize it because you don't really need to see it. I'm going to get rid of this one too. Actually, no, I'll talk about that one. So this one would have gone up. So let's say the right path is this one. So it has 5 children. So that's 1, 2, 3, 4, 5. So 3, 4, 5. Now, these would have more children if I didn't, cancel out these roots, but we don't really need to show them because we know they're not going to really do anything. We're really worried about the most important paths. This one's the left path. We'll say that that's this path right here that I drew out. So it'll have its first child, then its second child, then its third child. Then the next one is going to reach. It's going to make it. This technically should have one more child. Oh, you can't even see that though. Sorry about that. I'll actually move it up here. So this one's going to reach the end. And it will reach it first. I just drew this one out first. So it's going to return whatever value's in here. However you want to indicate that you reach the end and it requires X amount of moves, and this is how you do it, this is going to be returned under this branch. And that's how using a heap, well, that's very much so simplified. I just would love to say that. But that's pretty much how a heap would work in a pathfinding situation. And in this case, it's called a Dijkstra's algorithm, which was named after a person with the last name Dijkstra, but I don't know what his first name is. But good job, Dijkstra. You did great. So, cool, you can pathfind in it. But another way that you can do it is with organization of data. So, I want to pull up this thing you saw earlier. This tree right here. It's so pretty. I should name it again. What am I going to name it? I want to name it Gazpacho. I like that name. Gazpacho sounds cool. So pretty much, this is not a valid heap at all. But I want to show, I kind of wanted to hit two birds with one stone. I want to hit, I want to hit organization and sorting at the same time. So pretty much, this is not organized in any way, but you can sort it using a heap as well. And now I kind of need to share with you some math real quick. So there is a way to refer to a node's children. So if you, and in the end, also I need to make this clear, this is an array. Not an array, this is an array. Underscore. I mean, this is an array. So pretty much, this is going to be index 0, 1, 2, 3, 4, 5, 6. There you go. Those are your array. This is going to have 7 elements in it. And pretty much, the way that you're going to refer to a node's child, left or right, is this one is going to be 2i plus 1. So this is 0. 2 times 0 plus 1. There's 1 right there. 2 times 0. Then this one's going to be 2i plus 2. 2 times 0 plus 2, this one right here. And same works with this one right here. If you want to find the right child of this one, which is going to be 6, it's going to be 2 times 2, which is its index, which is 4. And then, so that's going to be 3, 4, this one right here. Ooh, sorry. Plus 2. It's going to be that one right there. I know, so crazy. And if you want to find a parent, it's going to be, let me make sure I get this right, I minus 1 divided by 2. Which is just the inverse of, this right here. But since it's an integer, if I take, 6 right here, since my 1 divided by 5, if I do 5, and since it's an integer, 5 divided by 2, it's technically 2.5, but since it's an integer, it's going to be 2. So there it is right there. And same works with this one. They're going to have 5 minus 1, so this is 5, minus 1, which is 4. Then 4 divided by 2 is 2. That's its parent right there. Ooh, just bang something. Didn't mean to do that. So, let me erase all this. So, pretty much the way that it works is that it just works backwards and it starts comparing everything. I'll make this a min heap. I'm feeling a min heap today. That's how I'm feeling. Min heap. Min heap. Exclamation point. So, that's what I want to do. So, it just works backwards and that's how it works. Works backwards and it does its thing. It compares everything until it's organized. So the lowest values are going to be at the top. And if this is a max heap, then the max values would be at the top, the larger values. So 6 and 7. 6. Guess what? I just want to say something. 6 is less than 7. So I'm going to move that. And then 2, ooh, that's less than 6. But by the way, we move from here. Move these two. We check this one off. Now, we move these because that's just not true that 2 is greater than 6. 2 is not greater than 6. So, now we're going to go to the next one. We're going to compare this. Is 1 less than 4? Yes. So we're going to change them. Is 3 less than 1? No. So we're not going to change it. Now we're going to go here. We're going to see is 2 less than 5? No. Is 1 less than 2? No. Then we're going to work backwards again. We're going to check again. It's recursive. I know. So crazy. So 7 less than 5? No. 6 less than 5? No. 4 less than 2? No. 3 less than 2? No. 5 less than 1? No. 2 less than 1? No. This is a completely valid min heap. Now, I would like to say that you may be thinking, why is the 4 here when the 5 is up here? And the reason why is because it doesn't matter what this value is. It only matters what its parent value is. So I could, I could swap these two just to, demonstrate. Then it would matter. Then it would for sure matter. Then you'd have to, run through this again. 7 less than 2, no. 6 less than 2, no. 4 less than 5, yes. 3 less than 4, yeah. We're going to move that. And this would still be a valid min heap. And if you wanted to make it a max heap, you would just do the same exact thing, same exact process, except now you're going to say if this one is greater, then you're going to move it, not if it's less than. So that's just a quick, overview over heaps. I got a lot of this information from geeksforgeeks.com. God bless their souls. If you want some more information about them and, heaps in general, they are a great source. So I hope you learned a lot from Gazpacho and Bernie. They really love to help.